sometimes leads you like doing the programming in somebody else's kind of leaves you kind of like that. But yeah.
Speaking of which, is there a way of changing the number of spaces put in when you push tab?
Yeah.
Stop equals, or will you want to expand tab if you want to do space rather than tab here?
Oh.
So for me,
yeah, that's a very important point. It's good for me.
Different things for different settings.
Okay.
yeah, maybe I have. Yeah, that's it. I have it down in my. I have it down in my C section. Yeah. So shift width is that?
Yeah. Shift width and tab stop.
Yeah, shift width is if you do a shift with a greater than or less than, how many spaces it'll move. But expand tab tab width and soft tab width are two commands. If you have expand tab set.
Oh, yeah.
Yeah.
Okay.
Tab width shows you is how many spaces it'll display for a tab character, but not how many spaces are actually there. If you set expand tab, it'll actually convert a tab character into spaces.
Yeah, I think Smart Tab does that too. Because
Yeah.
now I see down here I have no Smart Tab in my Makefile, which is necessary because Makefile actually wants an actual tab character before the command. Anyway. VI. All right, let me turn these back. I have an answer key up here if you want to look at it. And for the problems 1 and 2, particularly for problem 2, you may see like a massive diagram on your paper as I try to figure out what you did. And actually, towards the end, I just was doing the diagram for everybody just to make sure that I knew what you were doing. But that said, the possibility certainly exists that I made a mistake. So please do double check that. If you think you nailed it, let me know. Oops. I'm stepping on a wheel. Oh, wait. Couldn't stand. Instead, there he is. Yoma.
It really.
Tom. And Alexander. Okay, that's everybody that's here anyway. So there's a new assignment online, not surprisingly. It's kind of nice to get back to actually talking about programming rather than talking about tests and so forth. So the next homework is due next Friday, and you'll be writing something called a bitstream class. And the main purpose of this class is to emulate the writing and reading of bits to a file. I say emulate because the smallest addressable space in either RAM or in a file is a byte, 8 bits. So you can never write less than a byte to a file or read less than a byte from a file. You can never write or read less than a byte to memory. The smallest addressable space in most computer systems, every computer system that I'm familiar with, the smallest addressable space is a byte. That's not good enough for us. Now, we're about to write a compression algorithm based on Huffman compression. And Huffman compression relies on being able to represent information in arbitrary width words. What do I mean by a word? A word is a chunk of bits that represents something. I want to be able to represent stuff using 5-bit words or 10-bit words or 15-bit words. The reason is we are going to go through files and we're going to do what are called frequency counts on the bytes in the file. And we are going to re-encode those bytes, right? To encode a byte takes 8 bits, right? Okay. And that's a generic encoding. It doesn't really take into account the information that you're actually encoding. The Huffman algorithm is going to go through your file byte by byte, and it's going to do a frequency count on all the bytes, right? How many different bytes are there? The 256 different bytes, 0 to 255. And it's going to go through your file, and it's going to count all the 0 bytes, all the 1 bytes, all the 2 bytes, all the way up to all the 255 bytes. And you're going to essentially build a histogram of frequencies. Right? How many times does the 32 byte happen in this file? How many times does the 125 byte happen in this file? Whichever byte is the most commonly occurring byte is going to get the shortest re-encoding. So you're going to say the most popular byte in your file is 125. You're representing that with 8 bits. What I'm going to do is I'm going to represent it with 2 bits. And now suddenly I have reduced the amount of information required to represent all of those 125 bytes, all of byte 125. I've cut that down by 75%. Right? I've gone from 8 bits down to 2 bits. And then the next most common byte is going to be probably, oh gosh, it's been a while since I've thought about Huffman. I think the next most common byte is also going to be 2 bytes. And then the third most common is going to get you up into 3 bits, and so on. And what you're going to do is you're going to, the codes for each byte are going to get longer and longer as the byte gets rarer and rarer, or less frequent. And you get compression out of this. For an ASCII file consisting of typewriter characters, Huffman guarantees you 50% compression. Any idea why that might be?
Because all the typewriter characters are in a pretty small range.
All the typewriter characters are from 0 to 127, right? And so you can compress ASCII files really well with Huffman or with other encodings, because you're using a whole byte to sort of represent. Anyway, so there's that. 50%? No, sorry. 12%. Being a dummy. You only save 1 byte, 1 bit, 1 bit, right? 7 bits.
That's a hell of a lot of
Yeah,
compression.
I'm thinking half of the table, but no, it's you go from 8 bits to 7 bits. You only need 7 bits to faithfully represent all of the typewriter characters, right? My bad. So that knocks you down by 12%. Still not bad. And usually it's better than that, because there are lots of E's and S's and T's and lots of spaces. And so there are high frequency bytes that are going to get you even better compression. All right. In order to get real compression, before we go there, we have to be able to write bits to a file. Let me show you what this week's program. Let's look at this bitstream class. So the bitstream class is comprised of a byte buffer and an output bit position and an input bit position. This bitstream class, it's set up to either read bits from a file or write bits to a file, not simultaneously. You can't do that, but you can set it up so that it can read bits from a file, and then you could declare another bitstream object that can write bits to a file. Evan?
Just to be clear, by write bits to a file, you mean 1s and 0s?
I mean 1s and 0s, yes. And let's go down here and look. The way that this thing is going to work is it's going to use a byte buffer. So there's going to be a byte inside the object. And you're going to use the stuff we talked about last week about setting bits and reading bits. Let's pretend we're going to write bits to a file. And we know that we're not allowed to write a single bit to a file. We're only allowed to write a byte. What's the solution?
as you write bits, store them in a byte until you have 8 and then write another byte.
Simple as that, right? So you start off O-bit position, so we're writing to a file. So the output bit position is 0. So the first bit that you're going to write, whether it's a 0 or 1, is going to go into the 0 slot, the least significant, say. And then when you write that bit, you're going to increment O-bit pos to 1. And that's waiting for the next bit. And then you write that bit and you increment O-bit pos. You get all the way up to 7. And you write that bit and you increment it, and it wraps around back down to 0. But before you do that, what do you do with this byte? Flush it. Send it out to the file. Because now you have a whole byte of bits that you can write to the file. You flush it, and then you reset the O-bit pos to 0, and you just go back across. And it's really just a process of filling the byte and writing it, filling the byte and writing it, filling the byte and writing it. The only slightly iffy thing is your program ends and you've written 3 of the 8 bytes, 3 bits of the 8 available bits. What do you do then?
Make sure you print it to the file before you quit.
Yeah, make sure you manually flush the thing because it's not going to automatically flush. You could write a destructor that would automatically flush, but I intentionally did not do that. Yes?
If you were to write like a close function, would you do that there?
Yeah, that would be a good place to do it. There's lots of different places to do it, but I just left it as an explicit flush in this homework assignment. Similarly, you want to read the first bit from a file. Well, the way this thing starts up is it reads a whole byte from the file, and then you have the O-bit, the I-bit pos, the input bit position, and you just read those bits, and when you run out of bits, you go back out to the file and you grab the next byte and you reset and you read. Grab the next byte, reset and read. So you are constantly keeping O-bit pos updated or I-bit pos updated, depending on whether you're reading or writing to a file. Okay, let's keep reading here. Put bit will put the first argument C there is really just a 0 or a 1, input B, and it's going to put that thing into the output file stream, some file that's sitting on the hard drive. You don't see all of this stuff with the byte buffer and bit pos and all that stuff with put bit. Put bit is stick a 0 in there and a file handle and you're done. Stick a 1 in there and a file handle and you're done. And internally, it takes care of the buffering and the writing. Get bit. So this is if you're reading from a file instead of writing to a file. Reading from a file, you pass the first argument by reference, and then the second argument is the input file. If you say get bit, you're going to, let's see here. I'm trying to figure out what my bool get bit did.
Is that going to return the value of the bit as a true or false?
I think what it does is it goes false if you've reached the end of the file. I can't remember. I'll have to look at that.
Yeah, it's probably false if there's no next bit.
That's true.
I think that's what I wanted because then I can just keep reading until I run out of bits. Okay, and then the last two are put int and get int, and this lets me put an integer out to a file in any number of bits that I like, as long as the number of bits is big enough to hold the integer, right? So, for example, I could put int 255 as long as b were bigger than or equal to 8.
And the rest are just be zeros.
Exactly. And similarly, I can go read an integer from a file. I can get 10 bits from a file and convert it to an integer with the getInt thing. Why do we want to do this? We want to be able to put whole numbers out to a file in variable word length, and we want to be able to read in integers from a file in variable word length.
let's play around with this a little bit. So let me just show you what I'm looking for in terms of a running program for this assignment. Oops. And let me see what's in test.text.
What's all that fancy stuff in Shell?
Hold on for a second. Sorry, what's the question?
You did like CD 270 and then it still had that popped up on the next line.
She hit tab and it showed the other.
Oh, okay.
So it's offering me possible completions to this, which are really just the subdirectories.
So you weren't actually pushing enter.
I'm hitting tab,
Okay.
and then I can continue and hit tab, and then yeah, I'm a tabaholic. I mean, I don't want to type one single. I'll hit tab 1,000 times before I'll type one stupid character. Okay, in this test file, there are 3 characters. There it is right there, 3 bytes. There's B, A, and a line feed, the carriage return. So here's bit test. So I'm going to set the input file name, and it's test.text. And here's list the input file. Oh, sorry, I need to set a bit representation first. So I'm going to set a bit representation of 8. This could be a little more user-friendly, but... Oh, I did say bit rep set to 8. That was friendly of me. Okay. Now that the word length is set to 8, if I list the input file 4, I get 98, 97, and 10. 98 is B, 97 is A, and the carriage return is 10. So it read the bits from the file. It read 8-bit chunks from the file, converted them to integers, and printed those integers out to the screen. All right. Just so that you believe what I'm doing here, let's go here. ASCII binary.
What happens if we read it out as 7 bits?
Yeah, that's what I'm going to get. I want to get to that a little bit here. I want to explore this a little bit. So here's B. What happens if I set the word length to 4 and I list the contents?
Should get 6162.
6162. I think it was BA.
Oh, it's
Yes. So 6. Hold on for a second. Yes, 6, 2, 6, 1, and then where's 10? Oh, I don't have 10 on here. Does anybody happen to know what 10 is in binary?
0 or 1 0.
Yeah.
So I'll get a 0 and a 1 0 1 0, which will be 10. Yeah. Okay, let's see if that actually works. The only doubt I have is whether the bit order, but so I'm going to quit this just to make sure that I'm starting from a clean slate here. Let's get the input file, and let's do the bit representation to 4, and then list the contents. Okay, so it's doing the least significant first, and then the most significant. That's what I wasn't sure about. So least significant, most significant for B. Here's B. Least significant is 2, most significant is 6. 2, 6. And then here's A. Least significant is 1, most significant is 6. And then here's the carriage return. Least significant is 10, most significant is 0. Okay? I'm honestly not sure. Let's see. There are how many? There are 24. There are 24 bits in this file, right? What I'm worried about is I haven't tested the robustness of my program. I'm not sure if I can read from this file in a word length that doesn't divide the total number of bits. I might be able to, but we could read two 12-bit words and see what we get. Yeah.
That says n greater than 1. So is that how the whole or the assignment is as well? And would that be?
Yeah, you can't. You're never gonna be using one bit representations.
Well, wouldn't it just print out the entire file in binary then?
Yeah.
Okay.
And it might even work. I don't know. It's just that in Huffman, you're never going to be dealing with anything less than 2.
So print it out half back.
Yeah, I have a feeling.
Piecewise backwards.
I have a feeling once I'm at the end of the file, I'm not resetting the file, so I just have to restart. 1 test.txt 312 4.
And then default.
So you can verify that these are the right values, but it is reassuring at least that we only got 2. Right, there are 24 bits in the file, and I decided to read a word length of 12 bits, so I got two words.
But you're saying if you decide to put in 5, you can program like that?
I don't know. Let's try it. And 3, 5, 4. Looks like it's okay. It gets a little hairier trying to make sense of these numbers. We can at least try to make sense of the 2. So there's B, and we want 5 bits. 1, 2, 3, 4, 5. So that makes sense too. Now what's this? This is 1 plus 2 is 3. So yeah. Okay. So
Everybody sees what it's doing? This is a really fine level of control over the information in the files.
Let's write some stuff out to the file. Okay, so let's do. Let me quit this thing first. And I think if I just set the output file name, I'm going to overwrite it. So let's do that. Yeah. Let's set the bit representation back to 8. And let's write some stuff to the file. I haven't set B yet? I thought I did. Oh, duh. 3, 8. There we go. Now 5. Yeah, exactly. Okay, just to make believe here, what was this? This is 98, 90, let's do 99, 110. And let's see what we have. Ooh, that's not good. Yeah, it does. I can't remember how it. Like I said, I just dredged this thing up. Okay, it might just be an empty. Yes, I bet I have to. Instead of doing Control C, I've got to. Okay, so set the output file name test.txt 3 and 5 and 99, 110. There we go.
What is cat?
It stands for concatenate, and in this circumstance, it is essentially printing the contents of test.txt to the screen, but you can do other stuff with it, like cat test.txt, and then I can put it into another file like blah.txt, and now blah.txt also has that stuff in it. But I can do it again, and now blah.txt has oh, I must have clobber on. Oh well.
Two greater than two.
I thought one would if I had no clobber on. Yeah, so two. Usually I run a shell with no clobber, but I guess I've got clobber on this one. Clobber means if you use one of these redirects on a file, it will wipe out the right-hand side file and replace it with the contents. Usually I have no clobber set, which means it would append by default.
It'd be really bad if you just typo in one instead of two.
Yeah. It happens. No. So you can see cat is a way of pumping information from one place to another, and it works on binary files as well. If I do cat on this binary file, I'll wreck my terminal, so I'm not going to do it. Because there are bytes in there that are non-typewriter characters, right? In fact, in this file, bit test, there are bytes of all flavors, right, from 0 up to 255. And some of those bytes are actually control characters to the terminal, which will cause it to misbehave. What the hell? Oh, so it actually worked. Oh, maybe putty is somehow more resilient than Unix, but anyway. Sometimes you can wreck the terminal by doing that. But there are the bytes. And this is literally just taking each byte and converting it to a character and printing it to the screen, except some of those bytes don't convert to nice characters. All right.
Are there visual representations of all the characters in the ASCII table?
Nope.
And that's why you get blah.
That's why I get blah. Yes, if I look at man ASCII, this character column here, right, none of this stuff has visual representations.
Gotcha.
And then there's stuff at the end too. Only one. I thought there was more than one.
So your terminal doesn't even
That's missing.
some sort of symbol?
Doesn't give it to real size.
Well, ASCII, that's extended ASCII.
Yeah, no, I know.
Yeah, okay. This is technically all of the ASCII table. All right. So let me just continue this demonstration, and let's repeat the same process that I was talking about earlier, except writing to the file instead of reading. Let's do a really interesting one, like let's do all right, let me think about this for a second. I don't know if my program will let me change my bit rep midstream or not. Anyway, let's just repeat the 4-byte word one. So let's write 6 and what's that, 3? I guess 5, 3, sir. 5, yes, thank you. Do you know the Monty Python holy hand grenade thing? Yes. Okay. Did you know that Eric Idle is going to be here for commencement? And last year, nobody wanted to be faculty secretary, and I'm one of those people that has like this strong sense of civic responsibility. And so I said, yeah, what the hell. And as faculty secretary, I get to give Mr. Idle his honorary degree. So I'm very happy about that. So sometimes karma does pay.
What's the degree in?
I don't know what, I can't remember if you go like letters and arts or something weird like that. It's it's an honorary degree, whatever.
Something useful?
He totally deserves it. I mean, I would give him as many degrees as he wanted. The guy is awesome.
The only one ever given.
Okay, let's just write 4 bytes out and call it a game here.
I want one of those. Thanks, Jimmy.
Okay, so I've got the bit rep set at 4, and I want to start writing some integers here. I don't know, let's try to put z in there. Well, no, I'm kind of used to the 6 thing. No, we can try to put z in there. That's, help me out here. Thank you. And let's do one more. This would be 9 and 5. It does, and it definitely does make sense. And let's put a carriage return in there, 10 and 0, and hit enter there, and let's hope for the best here. Yes. You can actually see what happens if we neglect the carriage return. Output file name. There you go. Test.txt. Bitrep 4. Write some integers. What did we say for z? 6 and 5. 6 and.
No, that's 10.
10 and 5. And then let's just forget to do that and write to the file and cat the file, and do you see the difference? So that line feed was not placed into the file, it's not there, and the prompt here is on the same line as the contents of the file. Okay. Yeah, I think we'll leave it at that. I won't do that. I'm just wondering whether I actually want to start this Huffman stuff or not. I think I'm going to wait. So let's look briefly at some of these. I'll show you my main program here so you can get an idea of how this thing is working. My main program is pretty straightforward. It has this simple menu loop that just runs until an empty response is received. In this case, it's the command.length equals 0 breaks. Uses getLine to get the stuff from the screen, and I'm not really sure why I used getLine. Again, I wrote this the last time I taught this class, so that's like 2008. But getLine will read the input line in as a string and put it in the command variable. A to I is not really necessary, but that was just me playing around again. A to I is ASCII to integer. So it takes whatever number I put in on the command line, converts it to an integer for my choice.
Wait, is that something you wrote yourself or something that's it?
A to I, no, I didn't write it myself. It's part of C standard lib, which is at the top here.
Okay.
So if you put in like a letter or something as your menu choice, it would just
Yeah, and it might have some nice error codes associated with it. I don't remember.
If I remember correctly, it returns 0.
Okay.
Everything.
But I guess that begs the question of what do I do if I actually have a 0?
Yeah.
So I can't remember what it does, but A to I is a standard C command, actually. It's part of the C standard library. So I get the line, I compute its length. If it's not 0, I convert that to an integer, which is my choice, and then I have this action function, which is not part of any class. It does the thing that it's supposed to do, and it's the class that we really care about, and it's the class that I'm not going to show you. But the idea is every time you write, you put a bit into a byte buffer. When the byte buffer's full, you write it out. When you're reading, you read a byte from the file, and you keep track of when you need to refresh that byte. I think I'm gonna just stop here actually, so get 10 minutes free. Any questions before we break? All right, if you have questions about the exam, I'm here. Otherwise, have a look at this program. Think about how to write bits and read bits from a buffer. And if anybody came in late, I've got 2 exams up here. Okay. So what did I screw up?
I mean, I think you're right that makes more sense, but that still works. Because the only time it would end up there is if it had tested n to be equal to 1.
Oh, does it still work?
It seems like it should. Because it'll only end up returning if n equals 1. So then it returns n, which has to be 1 for it to be at that point in the process.
Oh, yeah. Yeah, that was not worth a half a point. Okay, I'll fix that.
Not a big deal.
Yeah.
I had already set new node next to cursor next.
Got it.
And so new node's already pointing at this guy. So when I point at that guy and go prev, I successfully get to this guy.
Yeah. With the inductive. Yeah.
New node.
How did that work? Well, so okay.
New node next is cursor next.
At the
Might as well just assume to start that it's irreducible.
Right.
So then that's cursor next next.
Then you have at most n groups. Well, so the splitting field, you have to include.
Sorry,
all
that's
n
cursor.
Right.
Oh, good God.
Right. You can think of
I need to
the
write it down.
field
I'll check it.
as
Okay,
Alright.
I'm pretty sure.
the nth group. Right?
Was the only thing that was wrong with number 8 my order of things? Because I realized this is a really silly thing to do, but I wrote it out and then realized what I did and tried to justify it by saying that I was replacing the second character, not index 2.
Oh, okay. I just totally missed that.
Yeah. I wrote it all out and then was like, oh, that I would never we would never assume that 2 means that, but that's what I did.
Okay.
So,
That's fine.
okay.
Okay. Which is the inductive step. And then adding 1 to it. If you add an nth group to an n minus 1, you assume by induction that the n minus 1 divides n minus 1 factorial. Yeah. And now that group that you added has to be of degree smaller than n or smaller. Okay. So you've just multiplied something that divides n minus 1 factorial by n, so it must divide n factorial. Yeah. So then you know that it's irreducible.